All right, so now we're going to look at limits at infinity. On the far right-hand side of the graph and the far left-hand side of the graph, what on earth is going on there? So here's the list of topics we've been going through. So we're almost to the end here, folks. There's a lot of really important topics. Now that last video, infinite limits, was actually pretty short. It was only 7 minutes long because it was pretty easy to understand. I have a feeling this one's going to be a little longer because there's a lot of material here for me to go over, including asymptotes, horizontal asymptotes. You learned about those in Algebra 2 and Pre-Cal, and maybe you referred to a limit, but probably not. So we're going to formalize that today. So there's quite a lot here to go through, so make sure you go through the entire video to catch it all. All right, so what are we talking about when we're talking about limits at infinity? We are looking at situations where this guy right here is our infinity or maybe negative infinity. Now I've gone ahead and given you the graph so you can connect the numbers with the graph here because that's always important. So as we imagine plugging larger and larger numbers into here, if you think about a t-chart, here's x, here's 1 over x. Like if we plug 1 in, we get 1. If we plug 10 in, we get a tenth. If we plug 100, what do we get? 0.01, right? And if we keep going, what are we approaching? This is basically going to be 0 when we get to plugging infinity in. So that's how we want to think about the numbers a little bit. This is approaching 1 over infinity, which is essentially 0. So we say the limit is 0, and you can see that happening over here on the right side of the graph. You see how the outputs, 1, remember it was 1, and then 10 was 0.1, that's already off the graph here. So this thing is getting really close to y equals 0, which is this line over here. Now what about on the left side? That's what we mean by negative infinity. So if we're plugging negative infinity, if we plug negative 1 in, we get, let's do our t-chart again, x, 1 over x. If we plug negative 1 in, we get negative 1. If we plug negative 10 in, we get negative 1/10. If we plug negative 100 in, what do we get? Negative 1/100th. You see, we're getting close to 0 on the left side also. Let me highlight this here for you. So over here, we are getting really close to 0 as we imagine plugging bigger and bigger negatives in. Bigger and bigger negatives in. Okay, that's one of the ways to think about infinite limits, is just imagining plugging a huge positive in or a huge negative. Because 1 over negative infinity, it's going to be negative, but it's basically 0. So that's why we say the limit is 0. Okay, moving on. I think we beat a dead horse there, didn't we? This time I didn't give you the graph, but what does the graph look like? It's a parabola. And you guys are good at this. You should be able to picture this. It's just a left shift by 1 of a standard parabola, and it opens up. It opens up. So what's happening as the x values get bigger here? Are we approaching any number, or are we just exploding to like infinitely large numbers? Obviously, we're getting infinitely large numbers. So this has a limit of infinity because this right side, this is called the right side, it is just going steeper and steeper. So that is heading to infinity. What about on the left side? Is it going to negative infinity? No. If you travel this way on the x-axis and start putting bigger and bigger negatives in, it just gets higher and higher. So the answer over here is also infinity. Okay? And you can think about the numbers. Infinity plus 1 squared. If you substituted in, remember earlier in this unit, we talked about how you just substitute numbers in. What if you plug in a bazillion? What do you get? A bazillion squared is a big number. It's infinity. And same thing with negative. If you square a negative, you get a positive. Okay. Now, let's make it a little bit more interesting here. Make it a little more interesting here. Do you notice how we have an x on the top and bottom this time? So let's think this through a little bit. First of all, back in our Algebra 2 class, we learned that there's going to be a vertical asymptote here at 2, and we talked a little bit about that, I think, in the last video. So we know there's a vertical asymptote there. But we are really only wondering about what's going on over here at the far right of the graph, and then in the next one it's going to be what's going on in the far left of the graph. So let's imagine plugging infinity in. When we plug a bazillion in there, folks, does the 3 even matter anymore? Does the 2 have any effect, the minus 2? Does this have any effect on the fraction value, really? Not really. Not really. It's all going to come down to the 2 times infinity divided by infinity. And the infinities cancel, so we are essentially equal to 2 as we imagine plugging the numbers in. That's the value of the limit here, folks. We are approaching the number 2. So there will be what we call a horizontal asymptote over here at x equals 2, or y equals 2, sorry. Now let's go to the left side. What if we plug in negative infinity? Does that change anything? It doesn't always change. Sometimes it does, sometimes it doesn't. Does that change anything here? Well, we already said the 3 and the 2 don't matter, and the negative infinity would cancel the negative infinity, so we are still basically 2. So on the left side of this, we would also be getting really close to the number 2, so that's going to be a horizontal asymptote. All right, so I wanted you in this, we're going to talk about this more in a moment, but for right now, I really wanted you to think about the numbers and then just see what's going on in the graph, and we'll talk more about that in a second. All right, moving on. What about this? What about this? What's different here? Well, there's no fraction, right? There's no divide by x minus 1 or something like that. This is literally a polynomial. What's the degree of this polynomial? The degree is 5. Is that an odd or an even number? Ah, that's an odd number. So what happens when you plug an odd number in to an odd exponent? Ah, you get a negative. This term is the only term that matters here because, as we've seen before, it will literally dwarf the other terms because the other terms are going to be infinitely smaller than the first term. I know this is kind of blowing your mind, isn't it? I remember a lot of students would have some troubles with this kind of thing when I used to teach AP Calculus. So you just got to think about a really big, really small negative number going into this. So in this case, it's a really large negative. And if you raise that to an odd exponent, you get an even larger negative. You get a negative. So what is 1/3 times negative bazillion? Basically, negative bazillion. So this approaches negative infinity. The 1/3 really doesn't matter here, folks, because remember, infinity is literally the largest number you can imagine, but there's always that plus 1. So you can't say 1/3 of an infinity. That doesn't matter. You just say infinity. So negative infinity is the answer here. All right, now let me give you some shortcuts, because if you are taking the AP exam for calculus or your final exam in college or whatever it is, your teacher's going to put some examples with these 3 scenarios, and you don't need to go to your graphing calculator and look at the graph, folks. So let me walk you through the 3 possibilities, and you need to memorize this and you need to feel comfortable with it. All right, what happens when the degree on the top is the same as the bottom? You see how there's a 5th degree here and a 5th degree. That's the biggest exponent. We already said all of these things really don't matter when you are plugging in infinity. So what happens when you have 3x? It's basically equal to 3x to the 5th over 2x to the 5th. And then if we plug in infinity, you see how the infinity, the 5th, are just going to cancel? So I might as well just cancel the x's now. Oh my goodness. This is approaching 3/2, 1.5. So when the degree on the top let me start again. When the degree on the top and bottom are the same, it's the ratio of the leading coefficients. It's the ratio of leading coefficients. Coefficients, I'll go ahead and abbreviate that. When the degree on the top is the same as the bottom, you don't have to factor or do anything like that. You just look at those leading terms. In fact, just look at the leading coefficients and that's your answer. So 1.5 is the answer here. 1.5. This crazy function, as you start plugging in bigger and bigger numbers, it's going to be outputting numbers that are closer and closer to 1.5. All right, what happens when the degree on the bottom is bigger, or it wins? I like to think about this polynomial as being a polynomial that wins the battle. So again, this won't matter. We really only have to look at the 7th degree and the 8th degree. Now what happens when you have 2 x to the 7th all over 9x to the 8th? Well, these 7 factors, let me get a different color here, these 7 factors cancel 7 here, leaving 1 behind. So this is basically equal to 2 over 9x. Uh-oh, we've kind of seen this already. What happens when you plug x equals infinity in there? You get 2 over 9 times infinity, which is basically 0. Anything divided by infinity is 0. Anything divided by anything divided by infinity is 0. Why? Well, think about it. What if we took 2 pizzas and we divide it among the entire planet? How much does everyone get, folks? 2 pizzas, and let's just chop it up and divide it among 8 or 9 billion people. I forget what the population is now of the entire world. Everyone gets essentially nothing. It's 0. So this limit is 0 because the bottom won. So when the degree on the bottom wins, the answer is always 0. Isn't that easy? It's always 0 when the degree on the bottom wins. Okay? What about when the degree on the top is bigger? Well, this is also equally easy. It's going to end up being, the top will become infinitely bigger than the bottom. So in this particular example, you end up with 5x over 3. 5x over 3 on the most important terms, which are those first ones. So the answer ends up being not 5 infinity over 3. That's the same thing as saying infinity. Just a really big number, folks. So the answer is infinity. So when the top wins, the answer is infinity if we're talking about an infinite limit. When the bottom wins, the answer is 0 when we're talking about infinite limits. The only tricky one is when they're the same. But then it's not so tricky. You find the 2 terms with the biggest exponents and, oops, sorry about that. Find the 2 terms with the biggest exponents and you take create a fraction with those coefficients. You see how easy that is. Plenty to go through here, so don't tune me out just yet. This is really important. And I picked this example specifically because students would always argue with me in pre-cal about this. The definition of a horizontal asymptote is if you imagine traveling to the far right of the graph, if you are approaching a number, you've got a horizontal asymptote there. Same thing on the left. If you imagine plugging negative infinity, if you travel to the left on the graph, and that limit approaches some sort of number, a value that you can figure out. It could be 0. 0 is a number. It could be 3/2. It could be 2/4. You remember up here? Let me scroll back. I'll even show you. That first example today, I mentioned about horizontal asymptotes. You see how both of these are approaching a number. These are numbers. So on the graph, you see a horizontal asymptote there. You see a horizontal asymptote on the far right and the far left because the limit approached a number. So we say if that, or there is a horizontal, all right, hang on one second, horizontal asymptote at y equals L1 or y equals L2, whatever those numbers are. They might be the same. They might be the same. They could be different, though. I'm going to show you an example here in a moment where they're different. Look at this example. So I went on to Desmos and I graphed 2x over 3x squared plus 1 for you because I wanted you to see it. Do you see how the bottom wins here? So we know the answer is 0. So we know there's a horizontal asymptote on the right at 0, which you can see. There it is. It's coming in for landing on y equals 0 on the right. Now what about for the left? It's also, this was supposed to have a minus sign here. I apologize. What about traveling to the left? It's also 0, and you can see how it's coming in for a landing. Now why would students argue with me about this one? Because, Mr. White, it crosses the asymptote in the middle. Like if you were to extend this, it crosses the asymptote. It's not allowed to cross the asymptote. Well, back in, I don't know, 8th, 9th, 10th grade, when you first started learning about asymptotes, your teacher might say, it's a line that the function never crosses, but gets really close to, right? Gets really close to, but never crosses. Here's the thing is asymptotes or horizontal asymptotes are only over here and over here. All right, they're not in the middle. You can't have an asymptote in the middle. So it doesn't matter what the function's doing in the middle. It only matters what the function is doing on the far right and on the far left. All right, so there we go. We showed that there is definitely an asymptote on the left and the right at y equals 0 because those limits existed, because they were numbers. All right, so I got a couple little, we're almost there. I got a couple things I still need to go through with you. What about exponential functions? If we do an exponential function, which remember what exponential functions look like? They go up like this. They go through 0, 1, 0, 1. Because anything to the 0 power is 1. So as we travel to the right, what is this function doing? It is exploding northward. So this would be infinity. But what about negative exponents? You remember negative exponents are actually fractions. So I can write this, I can actually write this differently. I can write 1 over e to the x with a positive exponent. So if the denominator is getting infinitely big, then this equals 0, and you can see that on the graph. We're coming in for a landing on y equals 0, which is the definition of a horizontal asymptote. Now here, I've just changed it around. What about this guy? If you plug negative infinity in here, you get 0. Over here, if you plug negative of a negative, you end up getting infinity. So these guys match. They're the same question, folks. And then these guys match. They're the same question. All right, so that wasn't too bad, right? What about this question? Does it matter if I put a 5 in the front and a polynomial like this? No, this is still limit as x goes to infinity on a really big exponent. So this is equal to infinity in the end. If you plug, I guess I shouldn't have written this here. You're going to end up getting infinity out of this thing. What about, this one's tricky. Some of you might say 0, or you might say undefined or something. What happens when you plug infinity in here? This is basically equal to 5e to the 0 power. In fact, it is equal to that. What is e to the 0? 1. So the final answer is 5. The final answer is 5. Wasn't that a good question? All right, so that's e. Now, natural log is the inverse operation to e. So I just wanted to mention this real quickly. What do the graphs look like on this? Remember, it's flipped over. It's like this. and it has a vertical asymptote at y equals 0 because the domain is all real numbers that are positive. So greater than 0 are the domain numbers, and this thing just keeps going up and up and up. It goes up very slowly, but it is going up and up. All right, so what would the values be here? As we travel to the right, what did I just say? It's going up and up. So believe it or not, this is infinity. It's going to take a long time to get to a bazillion, but it'll get there. And what about negative infinity? Well, as we travel to the left, we are approaching negative infinity. Okay? All right. So, well, let me change that answer. Let's change it to does not exist, because over here the graph does not exist. What I should have done is the limit as x approaches 0, on ln x, that would be negative infinity. Yeah, let's say then that's better. One last thing, folks. I wanted to show you, and I promised that I would show you an example with different asymptotes on the left and right. So the inverse tangent function has a range that matches the domain on tangent. So if you recall, here's pi over 2, and here's negative pi over 2. Because if you recall, tangent goes from negative pi over 2 to pi over 2 to do its one period. So this graph is going to have asymptotes like this, horizontal asymptotes. And it's going to go through 0, and it goes like this. Goes forever. It gets really close to pi over 2 on the right, so that would be this answer, pi over 2 on the right, and then it has a different asymptote on the left, negative pi over 2. Negative pi over 2. So I thought that was a good question to show you guys, just to make sure you realize you can have different asymptotes on both sides. All right, well, I hope that this video was helpful. I know it was really lengthy. There's a lot of important information here that I wanted to share with you. So hopefully that was helpful. Make sure you check out all the other videos in this series so you can go in like a pro to that final exam about limits. All right, I got a few more videos to make. All right, until next time.